How's your this?
I'm good. Student partnerships going pretty good. How's yours coming?
We were like through with milestone numbers and we were doing 4 charts. So ours has a map. So a map, a bar graph, and like a tree map. So we have like 3 charts that are given a milestone. We have to make like 3 more and some more data mashing that we have to do.
Okay.
So it's really long few weeks.
Mm-hmm. Yeah, the next few weeks are going to be pretty intense.
We have like 2 assignments each week. We have like 2 more each week. And then we have like 2 projects.
Mm-hmm. It's tough to focus on the algorithms project when we have the homework to do it. I don't know how to read it. Homework takes me a long time. Yeah, I spend a lot of hours on it.
We usually kind of discuss. We have like a group of people on 4 or 5 minutes. So we try so maybe 5 or 6 together. If we finish more so that we can maybe like explore around 5 and then we can go on and discuss what we should do. So I think so if you want to join us.
When do you guys meet?
We meet at the ski building. That's on the weekends usually. And Sunday before the submission, we meet and then we discuss. Next time we have that, I will call
That would be helpful. I work with Mattia a lot. I work in the TA lab usually every afternoon. It's definitely helpful to talk to somebody. I get stuck pretty easy.
When do you meet which team do you
Yeah, Palm and S. Ron. He's been pretty helpful.
Like, we don't have that much confidence in those two yet. But either like ACL or State, like currently will have the workshop, and then all the work is like in a total panic of like, we have to submit. There is like no excuse. So we're like, oh, what do we do? What do we write?
entire Facebook data set?
Or
So our purpose is to like put a subgraph. So that is how the attack works. Right? You put a subgraph, kind of retrieve it, and then like find out what the words is coming to. Right? So we could do that with any graph. Right?
That's my point. I think just create. Because the Facebook, you could look at it as sort of a randomized graph anyway. It's just going to be a whole bunch of edges. And then in that Stanford data set, it says, okay, here's the Facebook graph. It has 4,000 nodes. I think it has 88,000 edges. So just to recreate that, I think just take I think what we're going to do is just make our own graph class and then just a loop and just create a whole bunch of edges. Yep, and just do them at random.
Because if you have any and you put in a subgraph, you will get this. That's what you want to do.
It's the same
Yeah,
thing.
it's the same thing.
You don't get any value from.
Yeah, it's independent of the data set, right?
Exactly. Yeah, because this is around the studios and we're talking about the algorithms and stuff.
we can have notes on that too.
I spent about an hour trying to get that snap stuff to work. C++ stuff. I downloaded the libraries.
I think usually some people feel like that. No.
how those libraries are, like this one, there's like how they have like libraries.
Really, so what we just run,
It's a string.
I'm sure I'm missing something.
the eventual steps that you have to take.
So I was trying to find.
Yeah.
And I look at it, it's like this. I find stuff with the C++ directories and include also. I mean, how this stuff. Early instructions. Just do it.
I was able to run it. But, it seems a little nuts, but I was able to get it running though, so,
That's a plus.
but I spent more than 1 hour on it. So what's
Is
your,
it- Well, this is, I was talking to, gentlemen here, they're doing the same thing.
Yeah.
I think that's my proposal, is unless you've got running regional. I guess the part two question is, if you got running, can you load the data set? Or what's that going to take? I don't know that, I'm assuming that they match up, so I don't know. If the data set, for instance, in the analysis. If not, go with the model, use that really model as Facebook data set. I mean, it tells us how many nodes, it tells us how many nodes. You can create a simple class that has a graph class that has nodes and edges adjacent to this.
Yeah.
And you just put a for loop in there, X number of nodes, X number of edges, and then you say you can model it. Basically, it'll be exactly the same. Algorithm,
Asking is a
I think it's a bit of a work. It's something you don't actually create. Just create 4,000 nodes, manually 8,000 edges, but you do it in numbers, it's something like faster.
no,
let's get started. So, last time we talked here, we talked about how to estimate the size of joints using, and also like how to estimate the filter selectivity using histogram. So here we only talk about how to estimate the size about like two joins. Joining two tables, like either base tables or intermediate results. If you are given the size of two tables, and so basically, if it's a special case, if you have a primary key and a foreign key table, so basically you are joining a foreign key and a primary key in two tables, then the join size will be just the size of your the table that has the foreign key, right? Unless you have nulls over there. If you have nulls and you are doing inner joins, then the null will not appear in your final results. Then there will be some reduction, but null could be some kind of statistics you could keep in your database so that you can take that into consideration. So in a general case, if you are just joining on a particular key column, A, not key column, general column A, and A is not a key, it's not a primary key, it's not a foreign key. Then, in general, you can estimate the size of join as this. Okay, here you times the number of tuples of both tables, and that gives you the size of Cartesian product. So all of that, you divide that by the number of distinct keys of A in S. Okay, so that's one possibility. So basically, if you have that number of keys in S, then for each of the tuple in R, you basically will have exactly n tuples S divided by n keys AS, right? So then if you times that, that gives you an estimate. Or alternatively, you can think it in the opposite direction, like you think that for each of the tuple in S, you consider how many tuples there are that joins this tuple in R, right? Then, if you are assuming uniformity and like everything have a match, then the number of join for per tuple of S is going to be n tuples of R divided by the number of distinct key in A in R, right? So then it gives you this result, and you always take the lower one. That is because like if you think about it more thoroughly, like if you do have one of the the larger table, it's not possible for it to match every key in the smaller table, right? So if you think about that, it's actually the smaller one is a safer algorithm for the join size if you are assuming uniformity. Of course, this can be off by a lot if your data is skewed. Like it doesn't conform to a uniform distribution, then basically you could have one particular key that has too many tuples. Like almost all your tuples in your table have the same key in A. Then basically you get a Cartesian product. That's the worst case. So this if you do not have any information, like you do not have histograms on your tables, then basically this is the best you can do. You just estimate, just assume they are uniform and guess the number. And it works well in reality. In just common case in reality. Like if you have a typical table that does somehow conform to a uniform distribution, then this will work well. But if not, like if you have a very successful shopping site, then maybe some of the commodity you are selling have so many counts that when you are doing a join on that particular item, you are going to get too many near Cartesian product results, right? Then this is off by a lot. All right. So the next thing we will consider. So we have only talked about how to if you have a single table plan, how do you materialize the feasible plan? Or if you have a two-table join, how do you choose the join operator for them? Right? That's something we talked about. However, in reality, you could end up with a lot of join operators in your plan. Right? You could be joining 3 tables, 4 tables, 5 tables, and so on. So how do we actually enumerate the alternative plans? right? So for that, actually, we basically we have a certain order to enumerate that. So let's first give a brief summary over like queries over a single table. So if your query only have a single table, then it's basically select from a single table. Then you will have where, group by, having, and order by, right? So then it's your plan is basically a linear chain, right? You have a linear chain of operators. Then basically for the bottom one, it's gonna be the one that involves an access method. Like you can read the tuples from a heap, you can read the tuple from an index. Then that's the access path. So basically, you consider each available access path for this particular table, that single relation, right? And you always choose the one with the least estimated cost, okay? And then, of course, if you have a chain of operators, that actually, so sometimes choosing the best possible access method doesn't necessarily yield the best plan, right? So suppose you are doing an order by, and you are also you have a cluster index over the table. Then even if like sometimes even if your cluster index may be slightly larger than your heap, but because it's already sorted, you do not pay an additional cost of sorting, so that will yield a better plan, right? So you have to consider each of these index method and consider the whole plan to calculate what's the minimal cost. So then only based on that you pick the one with the least estimated cost. So this is for just like single relation plans. Also, like when you are considering this, also you should consider a lot of things we've already discussed, like predicate push down or like projection push down, something like that. So that you can reduce the cost of your join. Your query. Okay. So that's for single relation. A single relation is a little bit easier actually in this case because basically you have a limited space to search, and the space is usually not too long, so that you can actually write that for every case. So that's good. Then how do you actually estimate the cost? So suppose we are just using the IO cost. We are just counting how many IOs we are doing on this table. Then if you are using an index on a primary key that matches certain selection predicate, then the cost would be just the height plus 1, right? Because you are searching for a primary key, a specific primary key, then basically you just traverse down the tree and fetch the corresponding the plus 1 actually counts for the unclassed index. If it is an unclassed index, then you plus 1 to fetch the actual record, right? So that's plus 1. So if you have a cluster index that match one or more selects, like you could have multiple tuples that satisfy a certain predicate, then the cost would be just this n pages I is the number of pages in your data leaf level. Okay, the number of pages in your leaf level, or the number of pages for the data entries. Okay, so then if you have a cluster index for that, the cost will be just the cost for that plus the number of pages of R. If you add them together and times the selectivity. Okay, so that's the estimate. Or if you have a unclustered index, then basically you pay that for each of the fetch. Okay, so basically here for cluster index you have a bunch of data entries, right? So when you are scanning through the data entries, you only need to fetch this bottom, like the heap pages one at a time, right? So since it's like, because here cluster is basically almost cluster, it's not necessarily, so if you still use alternative 2 to build a cluster index, then you still need to traverse down the record ID links. But it's just because you have this buffering effect, so each of the heap page doesn't get to fetch twice. You just almost fetch them exactly once at a time. So then, so that's why you add together the number of leaf level pages in your index and the number of pages in your heap file. And that, if you times that with the selectivity of your predicate, then you get how many tuples, how many pages you are fetching. That's the number of IOs. Okay. But if you do have an unclassed index like this, then basically the links are going to be scattered around in your heap file. Okay. So basically, the worst case would be you can place like a worst case analysis on that. Then basically the number of page fetches is going to be the number of pages for data entries times the selectivity plus the number of tuples instead of number of pages of your heap files times the selectivity. Okay. So that's because for each of these matching tuple, you do need to actually fetch a fresh page for reading that record. So that's unclassed index. So, or if you are just doing a sequential scan of file, then the cost estimation is easy. It's basically just the number of pages of your heap file. Okay, you just scan everything once. And so, if you do have a non-classed index and you are imposing some kind of selection predicate so that you can use that, it's a matching prefix of your search key, then you can use that. But the end result is not necessarily better than sequential scan of the file, which is exactly something we've already talked before again and again. Like sometimes using an unclassed index is not essentially better than scanning the whole file, okay? Because of the factor here. Also, so if you do have a deduplication at the very end of your query, like if you do select this thing, then you do need to take into consideration the cost for duplicate elimination. What kind of duplicate elimination you're using? It actually depends on that. So of course, if you are using if you use a sort-based deduplication algorithm, then typically the cost would be just the cost for the access method, then apply then applying the filter. Yeah, that's typically just the access method. Then you pay a cost of external sorting. Then on top of that, you scan everything once. Then there's typically no additional cost for that. But in case if you do have something like if you have a non-cluster index or you have a cluster index where the key itself is a primary key, then once you begin to scan the file, you can do the deduplication on that. Right? So that's one possibility. Right? So if your range is already sorted, then you can already do a deduplication on that. Right? So that's one possibility to actually use. Okay, so that's the signal table. Let's see an example here. Okay, so let's say we have this sailors table where number of heap pages is 500 and the number of pages for the data entry is 50. Okay, and you have 40,000 tuples in total and 10 distinct readings. Okay, suppose we do have an index on readings. Then the cardinality of this particular query here, you are selecting the SID of the sailors whose rating is 8. Okay, so basically the cardinality of your result is going to be 1/10 of 40,000. That gives you about 4,000. Okay, 4,000. So basically the end result of this this query is going to be 4,000 tuples. Suppose if your index is actually a cluster index, then the cost would be just this. Okay, so 50 is the number of pages for the data entries, and you add the number of pages in your heap file. So that gives you 550, and sorry, 50 IOs times the selectivity. But then for each of the tuple, you are potentially paying 1 IO per tuple. Okay, so that's why you add n tuples of S. That's 40,000 instead of 500 in the case of unclassed index. Then once you add that together and times the selectivity, that's basically the number of pages you're going to fetch. Okay, so that ends up with 401 pages. That's like 8 times slower than a class index. If you have that. So if we have an index on SID, right? So then we do use the index on SID. Okay, if we have this class index on SID and we are trying to use this class index on SID, then since the key is not your search predicate, the keys in your search predicate is not a prefix of your keys in the index. So that means you cannot apply the filter directly on the index. You have to scan everything. Okay. So if you, in this case, you would have to retrieve all the tuples and pages. So with a class index, the cost would be just 50 plus 500. Okay, you cannot apply the filter, like use the index to apply the filter. Okay, with the unclassed index, if you do happen to use the index, that's to say you do not apply any optimization. You basically scan the data entries and try to fetch the data record once you have a new one. Then the cost would be 50 plus 40,000. Okay, so that's pretty dumb. You don't want to do that. Okay? And alternatively, you can just do a file scan. Okay, suppose you do have a heap file, then you can just do a file scan. Then that's 500 levels. Okay, so that really depends on what you have. Like, if you have a table, it's not possible to have a multiple class index. You can only have at most one class index. Okay, so let's say we have two scenarios. The scenario one is that we have an unclassed index and on rating, and we have a classed index on SID. That's a typical setting. Like because the SID is actually a private key, you usually build a classed index on that. But you have an unclassed index in addition to that on SID. Then in that case, if you have, then that basically means you have this one, you have this one, and you can also choose this one. So what's the minimum cost for that? That's going to be this 401, right? So if you just have a class index on SID and unclassed index on spreading, and you still have a heap file, then the cheapest plan would be just choosing this one using the unclassed index already. Okay? And that amounts to 401 IOs. Okay? And if you have, like, on the other hand, if you happen to have a classed index on rating and unclassed index on rating, and no index at all on SID, what you do? Basically, the cheapest plan would become using the classed index on rating, right? Then in that case, you only fetch like 55 pages in total. Okay. So basically, in query optimization, you look at all the available access paths, what kind of index you have, what kind of key file you have. Then you decide which one. You estimate the cost for them, and you decide which one has the cheapest cost, and you stick with them. Okay. And this is the process for optimizing a single table part. Yeah.
Based off of what choices you make further down the line, do you ever have to backtrack and make a different choice here, or do you just usually take the best every time?
Right. So that's something we'll need to talk about. Like, if you do have multiple tables, right? Different choices could yield different plans, right? And sometimes that's a tricky one. So I'll just talk about it a little bit later. Okay. Yeah. Right. So for queries over multiple relations, it must involve some kind of joints, right? So basically, you can form this into a tree, right? You can draw the plan into a tree, okay? Must be a tree structure. So the issue with the tree is that basically, because we've already talked about that, the joint can be applied in any order, okay? So basically, if you have n tables, there are n factorial number of possible orders for you to do the drawing, right? So then it's really hard to optimize over that. Okay, is if you just enumerate all the plans, is too expensive. Okay, so basically in R, the decision is that they only enumerate all the left deep joint trees. Okay, the left deep joint trees are basically something like this. You always join, so at the first level, you always join two base tables. Then once you have an intermediate result, you join that with another base table. Okay? So you always, so one of your table in your join operator is always a base table. Okay? And for here, like these guys are not valid left deep joins, although they might be cheaper than that. Just because the search space is so large that we just ignore that part. Okay, like Bushy flats. Like you could have an intermediate result as an inner table over here, and join that with C. We do not consider that. Okay, here basically the inner relation of your join operator is always a base table. So that because the inner relation is sometimes it's scanned once and once again, right? So if it's not a base table, then you could end up with like executing the subquery again. So you do not want to do that. So if you need to actually consider that, then sometimes you need to like materialize the drawing result or something like that. It makes the search space too large, so that it's not tractable to search. Okay, so yeah, so that's something called the fully pipeline plans. Okay, so in this way, basically you can fully pipeline your operators. You do not need to actually materialize anything. Okay, so the way you do that is if you call next on this topmost join operator, basically starts to like if you let's say you're using nested loop. Okay, so what you do is you call next on this to get the next tuple, right? And in turn call this to get the next tuple for the outer relation, right? And this produce a join result over here, right? Then we do not need to actually rewind this anymore. Basically, just keep that here, and you start looping through all the tuples in C. Okay, and then once you have one of the join results, you return that to its parent. Okay, that its parent now has a tuple at its outer relation. Then it starts looping through the B. Okay, you never have a blocking point in this whole pipeline, right? But or you do not actually need to like either you do not have a blocking point or you do not need to like recompute the drawing again. Like here, if you use this plan, when you call this, it tries to fetch a tuple over here, right? And then this join will fetch a tuple from the base relation C. Okay. Then once it starts to iterate through all the tuples from this join operator, it actually so for each of the tuple in C, you need to actually compute the full join of A and B once, right? So then the cost will be extremely high, or you can pay the cost to materialize the join result. That will also be prohibitively large, and if you do want to consider for every possibility, it's not too expensive. Okay. So how do we actually enumerate all the left-in plans? So here, I think something is actually not mentioned. So here we're making a decision here. it's also by it's for pruning the space. As you said, if we choose different different access paths for different method, like different based relations, you could end up with different costs, right? And that actually could affect the downstream operators. Like if you are scanning a index, B-tree index, then you get a solid file. Then immediately you can use sort merge join without paying the cost of external sorting, right? So that could have impact on the total cost, right? So the choice is actually you keep for each of the so basically for each of these base tables, you choose the cheapest plan, like you choose the cheapest access method. That's one, right? And then you also keep something that's cheapest, but not necessarily cheapest among all the possible access methods. But if it does have some kind of interesting order, then you keep that as well. Okay. So for example, here, let's go back to the example here. Suppose we are doing some kind of join, like joining sailors and reserve on SID, right? So one possibility is just use this file scan. Okay, that's 500 IOs. Okay, let's suppose you do not have any filter, then this is the cheapest plan because you just like scan the whole file. Okay, with any other indexes, you basically you need to pay additional cost for the data entries, right? But it could be beneficial for you if you do want to use the sort merge join, right? So if you were to use sort merge join, if you have an index on a class index on SID, and you are scanning the class index instead of heap file, although you pay an additional cost of 50, right? But you get a solid file, so that you can immediately to be used as the input to a sort merge join, right? So then you avoid the cost of sorting the file, like it could be like 4 times 500, right? So it gets a lot cheaper. Okay? So that's why you might want to keep not only just the cheapest plan overall, okay? So for each of these single table plans, right? You not necessarily only keep the cheapest access method, you only keep those that's cheapest among those that have the interesting order. Okay? Interesting order is basically on some kind of attributes that you might got involved in your downstream operators. So that's that. And also then, how do we actually enumerate all the left-deep plans? Okay. So let's first see how many left-deep plans do we have? How many left-deep plans do we have? It's actually going to be in factorial, right? Because like you basically impose a linear order of all the all the base relations and start drawing one by one. Okay. So that's in factorial. So even if you were to like search the entire space of this in factorial, it's still too expensive. Okay. So what we actually do is use a dynamic programming algorithm that searches this space in. It's still in the time complexity for that is going to be it's still going to be in factorial, right? No. Oh, sorry, no. It's actually going to be 2 to the power of n. Okay. So basically, for each of the subset of your base tables, you search for the cheapest plan for that, and you also search for the cheapest plan with some kind of interesting order for that subset. Okay. Then you can build on like all the plans for k tables to build a plan for k plus 1 tables. Okay. So in a nutshell, basically the algorithm works like this. In pass 1, you find the best one relation plans for each relation. That's basically choosing the access path. Okay. Then in pass 2, you so suppose you are looking at a subset of say R and S, right? So basically, you try to you just try to use R as an auto relation, then use S as a tuple relation, and try to figure out opportunities for that. So for R, it actually comes from pass one. Okay, for R, it comes from pass one. For S, that actually depends, right? So for this, you can actually reuse some kind of pass one result, but not necessarily. If you do like do some fancy stuff, like you apply some very complex calculation on that, so that it incurs additional IOs, then that's not necessarily the best case. You could always consider just keep scan or index scan like that, right? So then you consider whether to use R as the auto relation or S as the auto relation, and find which one is better, okay? Which one has the lower bound. And then for in a general pass A, where this A is actually smaller than or equal to the number of relations you have in the form. Okay, so then you choose an arbitrary subset of size n minus 1 of your subset of base relations, and then you draw. You already have the best pair for that based on pass n minus 1. Okay, then you join that plan. That joint result is the remaining from table in your form, okay, in your subform. Then you compute the cost for the node, okay, and once you have enumerated all the possible n choices of n minus 1 size subset of base tables, then you get the best result. Okay. So let's see an example of that. Right. Let's see an example for that. Let's suppose we are doing this join. We are joining S and R and B. Okay, on these two S and R joins on SID, R and B joins on DID, and we have an additional filter on B. Okay. Then, for simplicity, let's first ignore the interesting order. Like, if we do not keep any interesting order at all. Okay. So that's just for simplicity. But if you do consider that, then your computation basically needs to consider both the cheapest plan and the interesting order. So first, in pass 1, we search for the best plans for accessing each relation. Okay. So then, the result will be full reserve. Full reserve, what's the and sailors? The best plan would be just keep file scan, okay? Because you do not have any filter on that. Then the scanning, like alternative to B+3 next is always more expensive than that. Okay, so basically you can just use a keep scan. So then for boats, suppose you do have a B+3 and hash in Paris. What's the cheapest plan? Okay, that actually depends on the selectivity of this selection. Okay. As we've shown before, like if your selectivity is so high, then maybe using a class index is cheaper. Okay. Or if your selectivity is so small, that means that your end result is so small, then maybe an unclassed index is even better than keep-file scan. Okay. Right. So then, basically, let's suppose in this case, let's suppose our selectivity is very small. Then either the B+3 or the hash or color is the best access method for both. Okay. Then basically you record. So let's say you have a function f of the set S will be the cost of keep scan, okay, of S. Then you also have f of is basically the minimal cost for the subquery involving only S. Okay, f of S. And then f of R is going to be the cost of heap scan, okay, of R. And f of both, the cost of f of both is basically the cost of index scan on B, right? So that's the cost. And also you can also record the best plan in additional like other structures. Okay, so that's that. You have the best plan for the one related subqueries. Okay. Then based on that, we start to build all the best plans for all the two relation subqueries. Okay. So then we enumerate all the possibilities. Right? First, we need to build a plan for R and S. Okay. So that's what we write it that way. Okay. So basically, that's to consider for R join S. Okay. That's the plan for R join S. You consider all the possible plans for R join S and choose the cheapest one. Okay. So how do you compute that? One possibility is that you use the cheapest plan for R as the outer relation. Okay, so if you use reserve as the outer relation and stick with the best plan for R, that's a heap scan. Sorry, this one. And then you join that with the sales. Okay, the sales is the inner relation. Okay. Then what's the cheapest cost plan? Right. So you could do that using let's say you do that using an index loop. Okay. And then for the outer, then for the inner relation, you do need an index on SID, right? So you have that. Yes, we do have a B plus tree on SID or a hash on SID. Then we can use index next loop. Then you use this R. So you use the best one relation plan for R to get all the tuples out of it. Then for each of the tuple, you use an index next loop to probe the B plus 3 index on SID or the hash index on SID for S. Okay, and you can compute the cost for that, right? That's index next loop. And also you can also consider if you still use R as the outer relation and S as the inner relation, you still use the best one relation plan for R to sketch through all the tuples of R. But instead, you do not use the index next loop. Instead, maybe you use a nested loop, okay? Just a page or anything of nested loop. You can have another console, right? And you consider all the possible implementations for your join operator, so that you choose the best one. Okay? And that gives you the best plan if you choose R as the outer and S as the inner. Okay? And then you switch the role of the two. Okay? You use S as the outer, then R as the inner. Okay? And do the whole process again. You consider all the possible join implementations and find the best plan. Yep.
Wouldn't that not result in a left if we did the other version?
Right, but for past 2, it's actually okay. If you think, no, actually it's okay. So it's something like this. So if you, for past 2, it's less obvious, but if you think about past 3, okay, what really happens is that you choose one of the one smaller subset as the subplan. That's your outer, right? So you've already have a non-blocking pipeline like plan for that particular outer relation, okay, intermediate result. Then you can always use that as an outer because outer is only going to be scanning once. Okay. So for R, if you use an index scan on R, you can just like scan it once. You do not need to keep any intermediate result for that. Okay, that's one possibility. And then for S, what you use for that actually depends on what kind of access sensor you have. It's not necessarily come from the best one relation plans. Okay, it really comes from what kind of index you have, what kind of access method you have, and what kind of join operators you have. Okay, so basically this R comes from the F. Okay, so this is the corresponding plan for FR. But for this is really a cost of one of the access methods of S. Okay. So it's a little bit different. It's not really symmetric. Okay. But for the two, like for the past two, it's not really obvious. But if you think about that, so if you are clear with the process of searching for a particular the best pair for two size 2 relation subqueries, then for pass 3 and beyond, we actually do something like this. So in this case, we have R, S, and B, three tables, right? So you first start enumerating the size 2 subset of this subset, okay? And then use that as your autocorrect. So what that happens is really, so for example, for R, S, and B, you consider 3 cases. Case 1, R join S is the auto. Okay. Then your query is going to look like this. So basically, on the left, it's going to be R join S. Whatever plan you come up with, you choose the best plan for that. Okay. That's just the auto. Then for the inner, the remaining one is B. Okay. So you will need to join B to the intermediate result of R join S. Okay. So then on the left, this comes from the best plan of R join S. But on the right, for the inner relation, you still only consider all the access method of B, what kind of index you have, and what kind of join operators you have. Okay. So that's the asymmetric, why it's asymmetric. Okay, so yeah. So since we do not have any concrete numbers over here, I'll just leave it to like to your lab. Okay. In lab, basically, you have nested loop and hash join, so that you can consider different implementations of joins and and also you have different cost estimation. And you will need to implement this dynamic programming algorithm to come up with the best plan. And then for pass 3 and beyond, remember you always enumerate the one smaller subset of your current subset. Okay, and you actually need to do that for all possible subsets. Okay, and the number of subsets there is going to be 2 to the power. Okay, so yeah, let's talk a little bit about how to actually implement this, because you need to do this in your project.
One thing before we move on to that, why did you choose to use file size on 2 of the 3 relations?
Oh, why did we choose that, right? Yeah, so that's why, because if we assume we are using alternative 2 indexes, then basically the heap scan is always cheaper than the index scan if you do not have any index. Any filter. Okay, right? Because when you are scanning the index, you always need to additionally read the data groups. That's additional items. Okay. So that's why heap scan in this case is really cheaper. But if you have a case where you are using alternative 1 indexes, that's not necessarily the case. Or alternatively, if you have filters on both S and R, then the index could also be cheaper for the one relation.
Filtering on the SIDs, is that something you
No, the join conditions are not considered as the predicate. Okay, so we only consider the single relation filters as the predicate. That's the same. You could actually push down to the index, right? Yeah. So by no means this is the best plan, of course, right? So there are many tricky ways you can actually improve this plan, but it's just for a trade-off of efficiency and quality of plan. Okay? In this way, you will not end up with some kind of ridiculous plan like in the cross product, and then do all the filtering on top of that, right? That's a ridiculous plan. That's too expensive. In this way, you always end up with some kind of join algorithm so that you can minimize the cost. But it's not necessarily the cheapest plan. Okay? So it actually ignores a lot of like bullshit plans or opportunities like leveraging indexes. Like if you have a composite key index, then you could possibly do bullshit join that is actually cheaper than that. Okay? So a lot of things are missing over here. And also here, we are simply ignoring the interesting order so that we do not have the opportunity to use the sort merge join without sorting the data. Right? Or if we miss the interesting order because in the end we have a group by. If you do have an interesting order on SIE, then you can skip the sorting and directly apply the distinct algorithm as your end result. So those are missed opportunities in this approach. Okay, yeah. So let's explain this a little bit more for patch 3 and beyond. For patch 3 and beyond, so basically for each of the size n subset, you need to enumerate all the size n minus 1 subsets. Okay. So for here, we have only talked about use R join S as the output, but you could also use R and B as the output. Okay. So in that case, it's actually R cross product of B. Okay. Because you do not have a direct join predicate on R and B. Okay. But if you think about that, there are actually two choices. You could either forbid this. Okay, you can either say this cost, if it's a Cartesian product, we simply forbid that. We do not allow that. Okay, it's one possibility. The other possibility is you actually make it a valid plan and compute what's the size of it, okay, or what's the cost of it. That's also a possibility. And then if you have that, then basically it's going to be R cross product B as a black box. Then you join that with the S using some kind of join, okay? Something like that. And then that's the second choice. The third choice would be use S and B as the output. Okay. Then on the left, black box would be S join B, and it is the one that's chosen as the cheapest plan for S join B. Okay. Then you join that with sigma R. Okay. In this way, you are basically enumerating all the possible. You are enumerating all the n factorial lefty plans using only 2 to the power of n time. Okay. So that's the dynamic programming. So yeah, implementation wise, so in the project, I think there's a particular method you need to implement called order join. Okay. I'll open up the web page. Give you a little bit of hint on that. Oh, sorry, lab 4. So the lab 4 is already released today, and so basically in lab 4 you need to implement the cost estimating for base tables and for joins. Okay, that's the first part. And then you also need to implement the histogram, integer histogram only. Okay, string histogram you do not need to do anything about it. But if you do want to improve that's also possible. Okay, if you do want to do that, feel free to do that. Then for the integer histogram, it's a very naive one. Basically, it's just a fixed size. So sorry, not fixed size. The equal width histogram. You will be told how many, like there will be a budget, like how many buckets you should have for a range. Then on basically a static table, you are told to build the equal width histogram on that. And also, once you have a histogram, you need to implement some method for estimating the number of tuples in a particular range. That's the histogram. These should be pretty easy. Like you also have a class called table stats. That's the statistics in your catalog. Okay, so you need to keep some table cardinality or scan cost, a bunch of stuff in like implement a bunch of these methods in this class, so that you can estimate the cost of or size of your intermediate results. Okay. Then here comes the most difficult part. It's the joint cardinality estimation. Okay, that's the one we just talked about using the dynamic programming algorithm. Okay, so I think the algorithm you're gonna the method you're gonna implement is called order join. Right, there's a order join method. Which one is that? Anyway, the order join method is the entry point where we will call the dynamic programming algorithm. And the goal of that is actually given a bunch of relations. And basically you just have heaps. You do not have additional indexes on that. You just have heap files. Okay, so that will simplify things a lot. Then you apply the dynamic programming algorithm to find the best possible join order for that, which has the cheapest estimated cost. Okay. So then the algorithm, there's a pseudocode for that. Basically, you're responsible for like translating this pseudocode into Java. Okay, that's basically what you're gonna do. And there are some methods like cost and cost best plan. That's the cost, right? So these will involve a lot of methods you've implemented before in this project. Okay, like join size estimation or what's the cost for nested loop and the hash rate. Okay. You need to consider different alternatives. Then finally, there will be some utility methods like how do you actually in this pseudo code you will need to enumerate all the length I subsets of J. Okay, so J is basically J is gonna be a set of join nodes, all the base relations. Okay, and then in each of the paths, you'll need to enumerate all the length I subset of that the J length, the set of length J. Okay, so how do you do that? So you could write it yourself, or you could use the utility method we provided with the framework. Okay, so that will simplify a lot. Right. And also there's for each of those subset S of length I, you'll need to also enumerate all the d minus 1. Sorry, this is actually not d minus 1, it's I minus 1 subsets of that. Okay, this should actually be I minus 1 instead of d minus 1. Then you enumerate all those subsets. It's basically, remember in path 3, we have for each of the length 3 subset, we enumerate all the length 2 subset of that subset, okay, and come up with the best plan. So here you also need to enumerate a lot of subsets of subsets, okay. So we also have methods for that, so that it can be a bit easier for you to implement the whole thing. And finally, there's because this is a dynamic programming algorithm, you actually need to you have to remember what's the best cost for each of the plan. Okay, so you cannot so for example here for opt join, this should actually be a hash map or whatever map you're using. So basically, whenever you compute the optimal cost for a subquery, you record that best plan and its values, the best cost in that hash map, so that in the next pass you can directly reuse the results. Okay, you do not compute the results for one cycle. Okay, so that's the key. So any questions about this, about the algorithm? Okay. Yeah. So if you do have any difficulties in understanding the algorithm or like implementing the algorithm, let me know. I can give you a more thorough walkthrough of the code. Okay.
Will you have a project 5 as well after the final?
Yeah, we will have a project 5. It's gonna be released the Tuesday after Thanksgiving. Okay, and it will. So the deadline will be the weekend after the final. Okay, so that you have a little bit more time to work on it. But we cannot like extend that anymore. So basically, it has to be handed in by that day. Otherwise, we will not be able to finish all the grades. Alright, so that's the join order optimization, okay, and the algorithm. And finally, let's talk about nested queries. So as we said at the very beginning of this lecture, like the optimization lecture, the nested queries are actually treated as independent blocks. So basically, you implement them individually or independently without referring to other stuff. Okay. So, and then the outer block basically treats the inner block as a black box. Okay. So once you have a plan for the inner block, it's just a function that has a specific cost, and you take that into consideration for your work. Okay. So that's how nested queries are optimized. So I guess there are so many things in optimization, and it's really a very complex piece in database systems. What we have already talked about is really just a little peek into this massive, like extremely complex work. Okay, so so basically the key point, I think, as the most important takeaway message is that in database systems, you really need to take a lot of information into consideration. And for query optimization, the goal is not really to come with the best possible plan. It's not really possible, right? So the goal of query optimization, although people tend to chase for the best possible plan, but really the goal is to avoid the worst one. Okay, you do not want to end up with some ridiculous plan. Instead, you just want some reasonable plan that will produce your result in a reasonable time. So often the case, if you are using a database and you come up with some kind of complex join, nothing magical is going to happen. Like if you have a really expensive join, the database will not produce the join results in a reasonable time anyway. Nor will you, right? If you were to write the program, you are not able to unless you have some intuition into your data set, right? So that's why this is the case. So if you are using your later like career, if you are using a database to do a very complex query, you might need to think it through. Okay, it might not produce the results you want in a reasonable time. Instead, you should like reason about what if I give the query to the database? What's the chance that it can optimize that in a query? Okay. So that's something really important. That's the really important takeaway message for that. Okay, so but anyway, optimization. There are a lot of new directions in optimization. So, like the system R is basically a very simplistic way of optimizing things. Basically, it has rules and also those dynamic program algorithm for join ordering. But then you could also do adaptive runtime optimization, like as we said, sometimes the inaccuracy actually comes from the inaccuracy in join size estimation or like filter selectivity estimation, right? But what if you have run the query for a little bit so that you can get a peek about what's the true selectivity, okay? you know, once you execute the query for a little bit of time, you can estimate what's the selected. And once that's done, if that can be used as a feedback to your optimizer, then your optimizer can actually come up with a better plan so that you can just halt your current execution and restart better. Okay. So that's some other opportunities in optimization. So basically, that's something called adaptive runtime driven optimization, and there are some systems called ADIS that actually does that. And so that's actually not really the state of the art. So in recent years, as you know, the hottest topic in computer science is deep learning, right? Deep neural network, something like that. So people are also using a lot of learning techniques to try to optimize things. Like I know there's a bunch of work. So there has been an archived paper from Berkeley. They are trying to use deep learning to optimize joins, to optimize join orders. Okay, just as a substitute to the dynamic programming algorithm we proposed before. Okay, that's something. It's a recent trend that people are using machine learning to solve some hard problems in query optimization and database too. Okay. So that's the new direction in this field. Right, I'll just, yeah.
So, like in the past couple of decades, how many joins between how many tables can we do before like the dynamic programming optimization becomes too slow?
Oh, yeah, that's a good question. So in Postgres, I think the threshold is 12 or 30, something around that. Okay. So once beyond that, they switch. It's not necessarily the dynamic programming is too slow. It's just because even if you can run it in code, it doesn't yield a good plan. Okay, or it's just too slow. Okay. So yeah, there's a crazy work in this year's SQL. It's basically doing the query optimization, the join order optimization over thousands of tables. Okay, that's for guys from ETH, the ETH. So they were doing like they say we weighted this true query, like real query, real workload in some company, and they have a join that has like 4,000 something tables. How do you actually optimize that? Of course, nothing will work, right? So what they actually propose is that for very small joins, you can run this optimal solution, right? For left deep class. But really, you also want to consider the bushy plans because sometimes if you have cyclic joins, bushy plans could be better. Okay, so basically for very small joins, you could do that. Then beyond that, they basically, I think from my understanding, they basically split the optimization into phases. Okay, so later phases will basically depend on a specific choice for the previous phase. Okay, but it's not guaranteeing it's optimal. It produces good plans. Okay. That's one of the states. By the way, that group in ETH is like really good. They did a lot of really good job in this field. Okay, I guess that's it about query optimization. So after that, we will enter a field that's really, I think it's really exciting for a lot of people. Yeah, it's. I would say for me that's the most interesting part of database. Okay. So so then that's we'll come to the last piece of our lecture. Basically, we'll talk about transaction, concurrency control, and recovery. Okay. Yeah. So I'll just get it started. And so I'm not able to talk a lot in this lecture. Anyway, I'll give it a start. Okay. So transactions. So what is transactions? Okay, so the transaction actually, so basically in database, the transaction is basically a bunch of a sequence of operators you would issue using SQL. Okay, so why do we actually need the transactions? That's because we have two really independent requirements for our database. The first is we need concurrent database access. If you have a database system and you suppose you are using that for banking or for shopping, right, for a shopping site, what you really don't want to do is that you only allow one access at a time. Okay, so if all your customers are going to serialize their accesses, like only one customer can access the database at a time, then that's not going to work. Your business is not going to work. So we really need concurrent access to the database. Well, concurrent access means you have parallelism and concurrency, right? And then it's similar to what you have in your system program. Once you have concurrent access to like a variable or a certain memory, right? You can have race conditions. Okay, you could have concurrent modification and read at the same time, so that you cannot really easily. It's not easy to reason about what's the end result of your access. Okay, so that's why we need to somehow have some kind of control, so that we can easily reason about the effect of the database access. Okay. The other thing is, it should be resilient to system failures. So basically, the system failures we are talking about is like disk failures. Like if you are running a database over time, your disk is prone to fail, right? If it's a spin disk, it tends to fail after a couple of years, right? If it's an SSD, if you do have a lot of write, then it wears off. So that kind of failure you need to consider, right? And also there could be power failures, like if somebody shuts down the power, you lose all the data. That's not something you want, right? So your database should also be resilient to system failures. So the model of data access in database is basically you have a bunch of clients. These clients are actually typically they are not real clients of the business. They are basically programs to wrote. Okay, so if you have a website that allows you to inquire the balance of your checking account, you are not writing the SQL yourself. Instead, the programmers, the front end or back end programmers wrote a bunch of softwares, and they issue the request to the database. So for database, the clients are really just the softwares running on top of that, and their primary interface is SQL, right? Typically. And then, so if you do have a lot of concurrent access, there could be many issues like this. So suppose we have an enrollment table in your college. Okay, so basically you could be concurrently updating. So if the college, if the college name is Utah, and you increment the enrollment by 1,000, and you could also have a concurrent SQL update that says I want to increment the enrollment by 1,500. Okay. So what's the end result of this, right? So maybe you're saying one person wants to increment the value of enrollment by 1,000. The other person wants to increment that by an additional 1,500. Then suppose initially, so basically you can think of that as actually if you just have one record that has the same name Utah, you can think of that as a variable. Okay, so let's say initially the value of your variable is 0. What's the end result for that? The end result should be 2,500. Right? But if you do not do any concurrency control, then you could end up with 1,000, or you could end up with 1,500, right? How's that possible, right? So basically, something could happen here, like let's say let's ignore the part of index lookup. Let's say we just have access to this enrollment variable over there. To do enrollment, assign enrollment plus 1,000 to enrollment, you need to first read the value, original value of enrollment, right? Let's say this one, the first one read the value of x. Let's say x is just the enrollment value. The first transaction or the first statement reads the value of x. Then the second transaction reads the value of x. And then they compute what's x plus 1,000, x plus 1,500. Then what happens is that the second one writes back x plus 1,500, and the first one then writes back x plus 1,000. Then what happens is that the result of the first transaction overrides the second one. Okay, but in reality they should add together. But the first one actually is based on the old value of x. It's based on 0, right? So that in that way you end up with 1,000, right? If that's the schedule of your execution. And you could also have the two writes switched, and you could also end up with 1,500, right? Or if they are executing serially, then you end up with 2,500. Okay. So if you do not have any concurrency control, then this base you do not know what's the final state of the database after you execute these two calls. It's not really easy to reason about the status of the database if you do that. And you could also have tuple level inconsistency like this. So let's say you set the student ID, the student with student ID 123 to set the major of that person to CS, and then you concurrently update the application decision to yes. Okay, you are gonna accept the application. Okay, but what really happens is that let's say your database keeps a record like in row format. Okay, so originally your row is gonna look like this. You will have 123. Let's say its major is not available, and its decision is not available. Okay, and you start reading this. Let's say you do this. You first read the record. Let's say this is RIE, okay, or let's say this is X. You read the record first, and then the second transaction also read the record. They kind of make a copy of this thing. Then the first guy updates the major column to that to CS. So here, the first guy has a copy of this record as 123 CS and not available. Okay, and the second guy sets the decision to 1, but also on the old copy of that. So you end up with something like 123 not available and yes. Okay, and then you start running things back. Which one do you get? Right? The end result should actually be this student ID 123 is of major CS and is accepted, right? But your end result is either the decision is not available or the major is not available, or you could have both, right? So like none of them is not available. That's also a possibility if you serialize. But that's not something you want actually. These two cases. And then we could also have table level inconsistency like this. So let's say we are starting to accept applications of all the students with a GPA greater than 3.9. Okay? And then concurrently, if the size HS, I don't know what that is. Anyway, So if that's the case, you set you times the GPA by a 1.1 factor. Okay. Then you have this issue. Like let's say you have a bunch of students. The first guy, let's say the first guy has a size HS of 2,600, and its GPA is just like 3.8. Okay, and then you have a guy that's 2,600. His GPA is also 3.8. Okay, and then you have a student whose HS is 2,400 and whose GPA is 3.9, okay, or 4.0. So obviously, if you first do the first transaction, the end result is the third guy is accepted, right? But if you first do the second transaction, then all of them are accepted. But what if you interleave these operations, right? If you start updating the GPAs, let's say the first guy gets updated because 2,600 is greater than 2,500, right? You get 3.8 times 1.1, which gives you 4.18, right? So that's greater than 3.9. So as a result, it will get accepted by that. But it could also happen that so basically, this the first transaction have already read the old value of 3.8 before the second transaction gets a chance to update that field. Then the end result is that this guy is not accepted, this guy maybe, and this guy yes. So that's not something you want, right? If you do the second transaction first, everybody is accepted. If you do the first transaction, only the third guy is accepted. If you interleave them, you can end up with arbitrary results. That's not something you want. Okay? And also there's a multi-statement inconsistency. This is a tricky one, really tricky one. Like if you have a enrollment process, application process, and you have made a lot of decisions. You have yes and no's, okay? And you want to archive all those negative decisions, okay? Then you insert all the applications with a decision no into the archive and delete them from the application database. And then you count how many results are there in apply and how many are there in archives. So that should give you, if you add them together, they should give you the total number of applications, right? But what if you interleave them? You can end up with at most 2 times of them, right? Let's say you insert a bunch of no decisions into archive, but you haven't deleted any of them. Then at this point, you apply this count star or apply an archive, you could end up with at most 2 times the number of applications you have, right? Then that's the inconsistency you could have. So basically the concurrency control, so the goal of that is really we want to execute the sequence of single statements so they appear to be running in isolation. So we want to then have the effect of running them serially, but not really. We still want to interleave the operation so that it has a better performance. Okay? So that's the goal of having transactions and concurrency control in database. Okay. So it's 1:45. Let's stop here. See you next time. Yeah, that's small external consistency. Actually, there are people talking about that's something that actually has to be done. But if we are talking about its data is running in the
What if they're all like the same cluster, but then they're not?
Right. Actually, that's you can build a farm, like farm, or you can wait for and there's a system called Manner. They actually exactly they have